Hello, everyone. Thanks for tuning in. It is 2:01, so let's go ahead and get started with the workshop. So welcome to the latest session of NextGen Geospatial. This is the data science workshop series that we have every Tuesday, where we're talking about geospatial stuff. My name is Jeffrey Gillan. I'm a research data scientist here at the University of Arizona. I work at the Data Science Institute and also for the Cybers project. And let's just get right into the content here. Let me share my screen. Okay, so here's the course content that's here on our GitHub page. I posted it in the chat already a couple times, so you guys can get there. So let's go down to the schedule. All right, here we are. So the last three sessions, we've been talking about cloud native geospatial. All right, so that's the concept that we can do in entire workflows online in the cloud, and we can move away, in some cases, away from this download model where we have to bring large data files onto our computer to work on them locally. In the cloud native model, we can just keep them up in the cloud, work directly with them up there, and this can improve sometimes efficiency, sometimes sharing, make things more efficient for you. So today is, what is today? February 27th. So today we're going to continue on that theme. So this is the fourth topic in this cloud native series, I'd call it. So today we're going to talk about something called Zarr and Xarray. Zarr is it's a format. It's another cloud native format, and Xarray is the Python library that we're going to be using to analyze it. So let's go into the Zarr and Xarray content. Okay. So what is Zarr? Zarr is a file format, cloud native file format, but it's used for storing multi-dimensional arrays, and it's optimized for very large data sets that can sit in cloud storage and be streamed outside to other people. So this is very similar in concept to the other formats we've talked about. It's similar in concept to the cloud optimized GeoTIFF and the cloud optimized point cloud. So it's similar because these file formats can sit in cloud storage and they can be streamed out into client applications like a Jupyter Notebook or some other kind of software program. It allows us to work with large data sets without having to download them to our local computer. Okay, so let's start with some basics. If a Zarr is meant to be a multi-dimensional array, let's start with what is an array exactly. Some people's eyes gloss over when I say array. They're like, what are you talking about exactly? So when we say array, we're talking about a systematic grid of data. All right, so here's some examples here. On the left here is a single dimensional array, or sorry, a two-dimensional array. We have an X and a Y. So what does this remind you of? Maybe an image. In the geospatial world that I know, that is typically what an array is, or the most common example of an array is an image, like a GeoTIFF or a JPEG or a PNG, or any kind of digital image is an array. When it gets to multidimensional, then it's not just two dimensions, it's 3 dimensions. And so it could be an image, right, with an X and a Y, but also a Z. And that Z value, or that third dimension, could be some other kind of variable associated with the image at each of those cells. So Zarr for geospatial data. Let me just show some pretty common examples of what is a multidimensional array for geospatial. The first one that comes to mind is hyperspectral imagery. So here we have just kind of an image of, I don't know, conceptually of how you can look at hyperspectral data. You could call this a data cube. So we have, let's say we flew a drone or an aircraft over the landscape. We made a map, we made a big image. And so the image is a two-dimensional array. But for every pixel, we have all kinds of different bands or wavelengths. And they could be hundreds of bands. And so that gives it its third dimension. And so when we're talking about Zarr and multidimensional arrays, this is primarily what we're talking about, is large multidimensional data cubes that store very large data. It could be gigabytes in size or even larger. What's kind of cool about Zarr is that, see this large data cube is sitting in cloud storage somewhere. I can just grab a chunk of it instead of having to bring this whole thing over, download it to my computer or use it and store the whole thing in memory. I can just stream just a little chunk of it. And so Zarrs are when someone makes a Zarr, they define how big the chunks are. And so that's made by, the creator of the Zarr. I cannot make a chunk. If I'm just like a consumer or a user of the Zarr data, I don't have control. Hopefully they made the chunks and sizes that are kind of practical for me to bring over to my computer and not super big. All right, another example is meteorological data or weather data. And so that's actually what we're going to be using as an example today. And so there are a lot of data sets out there from NASA and others that are just very large, three-dimensional or multi-dimensional arrays that have all kinds of meteorological data like temperature, precipitation, dew point, temperature max, temperature mean. Any kind of meteorological data can be put in 2 dimensions, which is geographic space, but then 3 dimensions, which could include time steps. It can include like all those different variables I mentioned. And so these data can be very large, so large you don't really want to download them or move them around too much. They would kind of want to stay home. But with Zarr, we can just take a little piece of it, bring it over to our computer and work with it and analyze it. So if this concept of these big data cubes or multidimensional arrays sounds familiar, there are other formats that are quite similar. NetCDF4 is another one that does something similar, and also HDF5. So these have similar kind of features. Zarr is a little bit different. I think the main reason people use Zarr is the fact that it can be chunked. And so you can get little chunks of it instead of the whole thing. And also you can read and write in parallel. So if you're trying to do big processing across multiple computer nodes, like in a cloud environment or an HPC, I think Zarr can help you out with this parallel processing. And here we just have a list of some of the benefits of Zarr. It's nice because when you get a chunk, it is compressed. Don't ask me to explain exactly how the compression works. Not important.
That's a lot of empty spaces. Just still.
Carlos is giving some wisdom on compression. I'll have to learn that next year. Okay, so that's what Zarr is. It is a multidimensional array. Can be used to store geospatial data. It sits in cloud storage, and then you can grab it, chunks of it, to work with it in your local machine or through some cloud computing instance. So it's very similar to cloud optimized geotiffs or cloud optimized point clouds, just for large multidimensional data cubes. Okay, introduction to Xarray. Xarray is a Python library. And so it's similar to and extends the library pandas. It's specifically meant to handle multidimensional arrays, data structures. I'm not going to go too deep into what exactly it's doing, but just know that Xarray is the Python library that we're going to use to look at and analyze Zarr data. Let me just kind of go by some of these logistics here. Okay, instead of getting too deep into theory, it might just make sense to just start a Jupyter notebook and just start doing some of this practically. So for the example, to kind of give you an idea or to solidify your basic understanding of what Zarr is, we're going to be using data from NASA called DayMet, which is like daily meteorological data. And DayMet has gridded Zarr data, or gridded multidimensional arrays at 1 kilometer in resolution. And we're looking at the data that spans all of North America. And it has a lot of variables there. It's got minimum temperature, max temperature, precip, shortwave radiation, vapor pressure, snow water equivalent, and day length. So all of those variables, those are all housed in a very large Zarr file. So let's just launch Colab here and start clicking through it. Okay, so here we are. What we have here, if you've never used this is we are running code in a Jupyter Notebook, and Jupyter Notebook is just it's a coding, writing and running code environment that you access through your web browser. So that's what a Jupyter Notebook is, and we're actually hosting it on Google's computer, and that service is called Google Colab. So when we tap into it, we have ourselves a little virtual machine, and it gives us a little bit of space, a little bit of resources to do some computing. And we are just using their free tier. We're not paying for it. So they just give us kind of a little computer where we have 12 gigabytes of RAM, 107 gigabytes of disk space. And keep in mind that these Jupyter Notebooks on Google Colab are temporary. They are ephemeral. They're there to launch, to do some analysis, and then shut down. So after a day or so, this stuff is just going to disappear. So don't think that the Colab notebooks are going to persist on you, as they won't. So it's not a place to store your stuff. It's just a place to do analysis. So we're connected already. Yeah, let's kind of talk a little bit more about the data set. So this data set is it's actually stored in Oak Ridge National Laboratory. Let's see if there's anything interesting here about the DayMet data set. Daily surface weather and climatological summaries. Great. I think a lot of people use this data for lots of environmental and geoscience type of applications. Okay, what else? Stored in a Zarr format. We're going to use Xarray. Okay, so we're kind of jumping ahead, but in this sentence, it talks about Microsoft Planetary Computer, and it talks about spatial temporal asset catalogs. And so we are actually going to do a dedicated session to each of those concepts in the coming next month, basically. So we kind of skipped ahead, but I can kind of give you just quick definition of these things. So Microsoft Planetary Computer is kind of Microsoft's answer in some regards to Google Earth Engine. Microsoft has a lot of computing resources, and with Planetary Computer, they allow you to start a cloud instance, not unlike what we're doing right here in Colab, only we can get a much bigger cloud instance. And then Planetary Computer also has, they've aggregated lots and lots of data sets. They've curated and aggregated them and put them in one place. So they have a giant data catalog that we can look through. And that's similar to how Google Earth Engine works, is they have a big data catalog that they've aggregated from other sources, including NASA and USGS and all kinds of geospatial data, and brought it to you in one place so you can do big analysis on the cloud. And so for today's lesson, we're just tapping into one of their data sets, which is this DayMet data set. Planetary Computer did not originate that data. It's just a place where they've aggregated and stored it and distributed it. Okay, the next concept is Spatial Temporal Asset Catalog, or STAC for short, is the acronym STAC. And so what it is just it is a catalog to find geospatial data across the web. I would describe it as a metadata standard. So there actually isn't, it's not a database. The data itself can be anywhere. It's simply a web way to search for and find geospatial data in like a standardized way. So let me open this here. So Microsoft Planetary Computer makes all of their data sets in their data catalog searchable and findable in what we see here, which is the Spatial Temporal Asset Catalog, or STAC. And this is specifically the data set we're interested in, the DayMet monthly North American data set. And it gives us nice information about it, kind of gives a general description, puts it on a map, of like where the data set is. And then it tells us what they have, like assets, as in what are the actual data we can get. So we're going to be doing this in the notebook, but I just wanted to show you the kind of STAC catalog. Just get an idea what it is. We'll be doing a whole session on STAC catalog in a couple of weeks, so a lot more will be illuminated when I do that session. Okay, so let's go back to our analysis here. So yeah, we're using this DayMet gridded meteorological data. Okay, let's see, we're connected. Okay, we're ready to go. First thing we want to do is just install some libraries. So let's just start clicking through and installing things. And so when I install, I'm installing to the virtual machine. I'm not necessarily installing into my Python environment. That's why we have this exclamation point here that denotes we're running a shell command. And so we are installing to the, I don't know what you call it, the virtual operating system of our cloud instance right here. And so we're installing these because they probably are not already installed in the stock instance of Google Colab. Well, that one was. Looks like Tornado was already installed. Okay. Let's see what else. We're going to install Xarray. Okay, and then we're going to install PyStack client. So this is the library that allows us to search through a spatial temporal asset catalog, find things we like, and then bring them into our environment. So we use PyStack client is what that library is called to look at stack catalogs. Okay, then we're going to install something called FSS or FSspec. I'm not sure how it's pronounced exactly, but that's going to help us tap into the Zarr file that's in cloud storage and get some basic information from it. Dask. Dask is a library that helps us do parallel computing. So we're going to use that a little bit later on. And then CartoPy, I believe we're using that for map visualization. Okay, now that we've installed the required libraries, now we got to bring all those libraries in, load them into our Python session. That's what we're going to do right here. Okay, it takes a nanosecond to do. Okay, so next step is we need to go back to that spatial temporal asset catalog and find what is the URL, like where is the data that we're interested in. It was this thing here. So this is where it is. Let's see here, the assets. So I'm interested in the monthly North American DayMet and do it through HTTPS. Okay, so I can copy that URL. So that's the actual endpoint URL where the Zarr, where we can find the actual Zarr. Back to here. Okay, so I've already have it here. So let's just hit run here. So it's like, I'm just going to identify that is the stat catalog collection is what it's called that we are interested in getting data from. Okay, and I say, show me the assets in that collection. And it shows me these three. The one I was interested was the HTTPS version. And looks like it's stored in a Microsoft Azure blob. And so that is code name for cloud storage from Microsoft. They call it a blob. If you were Amazon, you would call it S3. So this is object cloud storage. So that's where the actual data, the Zarr is sitting in Azure blob storage. So that's its address. Okay, so I'm defining that, yes, that is the asset that I want. Not really sure what this field does, but let's just do it anyway. Okay, now this block of code is going to connect to the Zarr file that's in the storage and get metadata about it. This is called lazy loading, meaning we're not actually like downloading the data. We're not actually bringing the whole data into memory. We're just able to look at it, inspect what the metadata is remotely, find out, is this data set worth looking at? So let's do that. And it's this FSPec, that library, that's allowing this to occur. Okay, so this is all the data in that one Zarr file. So there's a lot here. So it's an array, 8,075 by 7,814 cells. So it's a fairly large array, and it has a third dimension of 492. And 492 is months. So this is a data set that goes from January 1980 to December 2020. So it's got 40 years of data, which is 492 months. So it is a big data set. So in terms of the different variables, let's see, it's got PRCP, which is precipitation, soil, not soil, snow, water equivalent, time bands. I'm not sure I know what that one is. Not sure what that is. Temperature max, temperature mean, vapor pressure. You can look at any of these individual variables and find information about this data set. So the total data set that we're looking at, the total Zarr is 115 gigabytes in size. So it's huge. Is this something you want to download? Probably not. You don't want to. But the creator of the Zarr chunked it. So it's in chunks. In this case, each chunk is 183 megabytes, which is a whole lot more, digestible. And instead of the full array size, which is this, it now has an array size of this. So that chunk is 2000 by 2000 by 12. Now that was a choice made by the creator of the Zarr to make it that size. I think it can be specified any kind of size or shape you want, but those are the chunks. And so when I am interested in an area of interest, then it will just give me all the chunks that then make up, my area of interest. So you can think of chunks kind of like tiles, like what we talked about in GeoTIFFs a couple weeks ago. When you're doing web mapping and you zoom into somewhere on Google Maps and then it loads kind of square by square. Those are tiles, and that's sort of similar to what a chunk is. It's just taking this big file and breaking it up into smaller uniform portions that are more digestible. So this Zarr, this DayMet, meteorological Zarr is a really big file, 115 gigabytes. It's chunked up, which is nice. So that was just us querying the data. We just looked at metadata and we got information about it. And yeah, it looks interesting to me. So let's get some of it. All right, so this little block of code is going to, let's see, it's going to select, we're actually going to bring some of it over in memory, I believe. And so I'm interested in temperature max as the variable, and I want to do it just for July 2020. So yeah, each everything is in months. So it's just month by month by month is kind of the granularity of the data you can get. You cannot get day. I think you'd have to find a different data set or like a different process data set to get every single day. But we're looking at the monthly averages for 40-year period. Okay, so in this block of code, we are looking for temperature max July 2020. And what else? I think that's it. And it's going to show me what that data is. Okay, so it's just 2 dimensions here. It's just 1 month, all of North America, and just temperature max. Okay. Thank you. So let's do a little bit of analysis. So that's just an example that we did previously. So for this one, let's select precipitation for June 2020, and we're going to compute an arithmetic mean. We're actually going to coarsen it because the data we get is 1 kilometer by 1 kilometer. But let's just do a simple analysis of actually make it 4 kilometer by 4 kilometer cells. And so we are coarsening the data. You could call that data resampling, is kind of a geospatial term people use. This is just a demonstration that we can get chunks and then do some kind of simple analysis with it. And then once we do the calculation, we can do a simple visualization. All right, we'll see how long this takes. Did it? Okay, it did. So it did that calculation. For all of North America, it made a 4 kilometer by 4 kilometer grid for precipitation for June 2020. All right, now I have to visualize it, and that's what this cell block should do. Okay, here we go. June 2020, we have monthly, so we have precipitation on the right here. Darker areas mean more precipitation in June of 2020. Wow, it looks like it rains a lot in the Yucatan Peninsula. Not so much over here in Arizona. So that's just an example of a basic analysis you can do. This started from a very large Zarr file of 115 gigabytes. We took a little chunk of it and we did some basic analysis and then visualized it. Okay, let's do another simple one here. So what this one is going to do, it's going to identify the 2 months with the highest precipitation average in the last 10 years. So it's going to look through all of the data and be like, which 2 months have the highest average precipitation in the last 10 years? Okay. I'm not going to hit play on that because I did this last night and it took like 10 minutes. So let's just skip it because I can't tell jokes for 10 minutes. So I already have the results here. I did this ahead of time. So it spits out this. It found that the 2 months with the highest precipitation in the last 10 years was August of 2016 and July of 2013. And so this is average as in like all of North America. So what does that mean? Nothing really, right? What's the average rainfall in North America? It doesn't mean anything. It's so general to be useless. But it's just a demonstration that you can do analysis and calculations with the data right here in your notebook using Zarr data. Okay, and if I plot, I can take those results and plot them. And that's what we have here. So on the left, we have precipitation for that August of 2016. And then on the right, we have precipitation for July of 2013. So apparently those are the 2 wettest months in the last 10 years. on average for all of North America. Okay, interesting. Okay, and that is all the code I had in this notebook. And pretty much all I had for today. Wow, that went a lot faster than I thought it was going to be. But yeah, we're trying to keep things simple. I see something in the chat here. Let's see. If you didn't specify Corson, would it run 1 kilometer? Yeah, it would. I did this yesterday, and I think it would take a while. You're going to have significantly more data. 4 times as much data, I think. Am I right? And it will just take a long. Yes, you can do that, Ryan, of course. Just for a demonstration purposes, I needed to make it run a little quicker.
It's 16 times.
16 times. Thank you for the multiplication lesson. Yeah, it's better when things are small for demonstration purposes. That.
So could that be done at the person for the 2 months of the highest precipitation?
Can you say your question again, please?
Could that be done like that portion? Could that be done to the chunk of code that says identify the 2 months with the highest precipitation?
Yes, of course. Yeah. We're writing customized code. So absolutely.
Oh, actually, I can see, I don't do Python. The notation is like really similar. It's just in the first one, it was all like entered each time. There was like a dot mean dot load.
Mm-hmm.
This is on the policy button.
Yeah. You can analyze in any way. This is just a couple kind of straightforward examples. I've never really worked with Zarr data personally, and so this is kind of neat learning about it. And yeah, I wonder if there's even like, I know you can use this for hyperspectral, but I don't know if there's hyperspectral like out there for me to just use. It seems like the most readily accessible or good example of this is in this meteorological data formats. Carlos, you were saying that Zarr actually originated not in geospatial, but in what, like genomics or something?
Yes, it was originated in bioinformatics. So all the data structure can be applied when you're studying different tissues and cells. And so you can describe all the characteristics or physical properties and chemical properties of cells.
Right.
So they needed a format to store all that information.
Right. It's an array of data, multidimensional array, and that data can be anything. It just happens to work well with imagery, geospatial imagery.
They have all variables of every location.
Yeah. Yeah, it's incredible. I mean, a lot of that is interpolation. They probably don't have a sample in every single place. They have samples everywhere, and then they're modeling to fill in the gaps, the geographic gaps.
Spatial interpolation is a whole new field.
Oh, it's a challenging one. And over those scales, it'd be quite difficult because you'd have to incorporate a lot of like topographic features, and like just because it's near it, whoa, it's 3,000 feet higher. That'd be a challenge at those continental scales. Okay, so that's what Zarr and Xarray are. Zarr is just a multidimensional array format. It's cloud native because it can be streamed from cloud storage into an application. Using Xarray, which is a Python library, you can bring in it and analyze it in a Python environment. You can bring in little chunks of it, so you don't have to download or bring into memory 115 gigabytes. You can bring in something a lot smaller. Yeah, and so that's it. Any other questions out in Zoom land?
I came late, but this was really interesting, and I really enjoyed that diagram at the end. That was cool.
Which diagram?
The one of the the wavelength. That's really great with the X and the Y and the
Right. Yeah, to me, it's a great way to visualize multi-dimension. It's not 2-dimension, it's 3 and even more. Like the Zarr that we use, the DayMet is like 6-dimensional, but I don't know how you make a 6-dimensional object.
For another galaxy.
Yeah, right. So yeah, very, very large data sets. Yeah, Zarr and these types of data formats are kind of new to me. I don't know. I did not include how to make one yourself because I think the applications are so limited, and it's hard for me to imagine very many individual researchers making Zarr currently. There could be in other fields, but in geospatial, it seems like it's more like institutional, people that are generating and distributing large amounts of data use this type of format. Okay, what else? Let's see. Carlos, NASA produces a product that assimilates all weather data, including soil and radiance.
Still does.
And is that also in a Zarr format?
I'm not sure. Must be. Let's see.
Could also be a NetCDF4 format.
Yeah, probably. That's the old format.
Okay, well, thank you guys very much for your attention. Let's talk about next week. Okay, next week we have spring break. So March 5th, we will not have a session. March 12th, which is also a Tuesday, we'll dive deep into spatial temporal asset catalogs, which we just touched on today. And then after that, we'll get into cloud computing. We'll do a session on Google Earth Engine and then planetary computer. Hold on, no, we're going planet satellite imagery and then Microsoft planetary computer. I'm gonna do something on drones, probably open drone map. And then the drone imagery analysis. I don't know. I'm thinking that's probably going to be some kind of deep learning thing. I'll get with Mithun. And then we'll finish with containerized processing pipelines. So thank you very much, and we'll see you in 2 weeks.